Okay, so let me start problem one. Oh, and if you have questions, type them in text box. Then I'll be able to hear the questions. I'll be able to read the questions. Okay, so um, form a polynomial whose zeros and degrees are given. Use leading coefficient 1. So we want a monopolynomial. So I have a 0 of -3 with multiplicity 2. So let's construct a function f of x. And so we have a 0 of -1 of -3. And so a factor of the polynomial is just x plus 3. It has multiplicity 2, so you just square it. And it also has a 0 of -1. And so we have a factor of x plus 1. This has multiplicity 1, and so there's no power. It says that the total degree of the polynomial is 3, so that is our function. Any questions about that? Okay. Next, I have a polynomial with 0, -5, so a factor is x plus 5, a factor of 0 of 2, so a factor of x minus 2, of 3, so x minus 3, and of 4, so x minus 4. And the total degree of the polynomial is 4, so I have 1, 2, 3, 4, and so that's our answer. Okay? For polynomial, list each real zero and its multiplicity. Determine whether the graph crosses or touches the x-axis at each x-intercept. Okay, so in this case, I have a 0 of x equaling -3 since we have a factor of x plus 3 and the exponent of x plus 3 is just 1. And so this is a simple root, so it has multiplicity 1. And it passes through the x-axis, so it goes through. Okay. Next, I have a root 0 of x equaling 7, since I have a factor of x minus 7. And this is x minus 7 to the fourth power, so it has a multiplicity of 4. Okay, so that means that it's not going to go through the x-axis. It's going to bounce off the x-axis, and so it just touches the x-axis. But it does not, just touches. The x-axis, but it doesn't go through it. Okay. Any questions about that one? Okay. Yeah, so an odd crosses through it, and an even just touches it. That is correct. Multiplicity. Um, choose the one alternative that best completes the statement or answers the question. Okay, so solve the problem. Which of the following polynomial functions might have a graph shown in the illustration below? Okay, so I look here, I've got a root at 0, so my polynomial should look like x. And notice that it passes through this root, and since it passes through the x-axis, it should have an odd power. And notice that when it passes through, it actually passes through um, looking like a line. So I bet it's a power of 1. Next, I have a root at 1, and it bounces. So it should have a even multiplicity. And so, it looks like a parabola. So I would imagine it's 2. Next, I have a root at 2. And notice that it looks like a line here. And so I certainly know it's odd, an odd multiplicity, because it passes through the x-axis. And it looks like it's just a regular line, so I'd imagine it has a power of 1. And so it is C. Any questions about that? Okay. Nope. Okay, so let's see. Write a short answer. So write a word or phrase that best describes, best completes the statement or answers the question. Find the domain. Okay, so to find the domain of f of x equaling x plus 2 over x squared minus 49, well, I set x squared minus 49 to 0. And so x squared is 49. So x is equal to plus or minus 7. And so the domain is all real numbers except for plus or minus 7. If he wanted it in your answer to be, say, an interval notation, then it would be negative infinity to negative 7. Actually, let me give some more room here. It would be negative infinity to negative 7, union negative 7 to 7, union 7 to infinity. So I'm not really sure if how he wants the answer written, but either of those will work. Any questions about that? No. Okay, let's do problem 6. F of x equaling 2x squared minus 4 over 3x squared plus 6x minus 45. So again, set the denominator to 0. I really don't care about the numerator, even if it has common factors. I really don't care. So let me set the denominator to 0 and solve for x. Let me divide by 3. So let me factor, bring down the plus, times minus is minus. I want two whole numbers whose product is 15 and the difference is 2. So 5 and 3. So I get x equals negative 5, x equals 3, setting these factor to 0. And so the domain of f is a set of all x's not equal to negative 5 nor equal to 3. So again, if we were writing this in interval notation, be negative infinity to negative 5, union the open interval negative 5 to 3, union the open interval 3 to infinity. And that is your answer. Okay, any questions about that? Okay, so let me do problem number 7. It didn't say to find the range. It just said find the domain. And so if it only says find the domain, just find the domain. Okay? Okay, so problem number 7 says use the graph to determine the domain and range. Okay, so we'll have to sort of see if you have a good eyesight. So the domain, well, it's going to be, notice that you have a corresponding y value for every value of x except when x is 0. And so the domain of this particular function is everything except for 0. Okay? And so it is negative infinity to 0, union the open interval 0 to infinity. And that's your domain. Now the range are the corresponding y values. And so notice that it's all y values except for this little gap here. And so you have a corresponding y value for everything except for this little gap between negative 2 and positive 2. And so the range is, well, everything up until uh, it doesn't seem to include oh, and it does include negative 2 and everything from 2 to infinity. Question. Yeah. Okay. Yeah, so it includes 2 and it includes negative 2. So it's everything except for the interval between between negative 2 and 2. Okay. Um, find the vertical asymptotes. Okay. And so let's find the vertical asymptotes. Actually, I think I might add a page here, a blank page, so I can put some stuff in here. Okay, so I want to find, so this is problem number 8. I want to find the vertical asymptotes for this. And so let's simplify this function. And so I have r of x equals negative 3x squared over x squared plus 2x minus 24. So let me factor this, factor the denominator. So it's x, bring down the plus, times minus is minus. I want two whole numbers whose product is 24 and whose difference is 2, 6, and 4. Okay, and I can't, oops, I can't really factor anything. Yep, it's 4 and 6. And negative 6, yeah. Okay, and so let's find the vertical asymptotes. By setting each of these to 0 and solving for x. So x is equal to negative 6. That is the equation of the vertical asymptote. And x is equal to 4. That is the equation of the vertical asymptote. And so you have to write them as x equal negative 6 and x equal 4. Okay? And so it turns out that each of these, for each of these values of x, you have that this rational expression goes off to plus or minus infinity near them. Any questions about that? Okay. Let me do problem number 9. Okay. Same thing. So x minus 7 over 49 x minus x cubed. So let's simplify this. Question? Yes, yes I can. Okay, that's fine. So let me factor out an x. So it becomes 49 minus x squared. But now I can factor out the 49 minus x squared. That's a special product formula. So I get x. Now let me put it down here. So I get, factoring out the 49 minus x squared, I get x minus 7 and 7 plus x. Okay. So, but notice that I could actually cancel these out. So I could actually cancel this guy with that guy. Except when I cancel it, one is the x minus 7, the other is 7 minus x. So they're of opposite sign. So if I do that, I get a negative 1 over x, and then 7 plus x. I'll just write that as x plus 7. Now, of course, I've changed the domain, but I really don't care that I've changed the domain because I'm only looking for vertical asymptotes. And so now I can set the denominator to 0. I couldn't set the denominator to 0 before because I could have had this cancellation, in which case instead of being a vertical asymptote, it could just be a place where I have a deleted point on the graph. And so let's set the, yeah, right. So that's why these canceled. So because these canceled, I actually don't have a vertical asymptote at 7. So let's set each factor in the denominator to 0. So I get x equals 0 is one vertical asymptote, and x equal negative 7 is another vertical asymptote. So in this case, it has two vertical asymptotes, and that's it. So it also has a missing point in the graph. It has a deleted point. Okay, so let me do. Did I miss one? Oh, I see. No, I'm looking at something else. Okay, so given the equation, give the equation. No. You don't have to graph. Not until they tell you to graph these. So in these particular case, you don't have to graph them. So give the equation of the horizontal asymptote, if any. Okay, so let's do that. Um, to find the horizontal asymptote, well, you'd look at the limit as x gets very large and see what these approach. Well, as x gets very large, this approaches as x is large. Well, it looks like, well, I have x squared plus 7x minus 9. Well, for very large values of x, this is very close to x squared. And I have a x minus 9. Well, for large values of x, that's just very close to x, which is an x. And so as x goes to infinity, this whole thing goes off to infinity. So this means that there is no horizontal asymptote. Because, oh, as x approach this thing, as x gets large. So as x approaches infinity, what do these y values approach? Well, they approach x, but as x goes to infinity, x goes to infinity. So this quantity here goes off to infinity, which is not a horizontal asymptote. It doesn't approach a value. That's what it means to be a horizontal asymptote. So for a horizontal asymptote, the question is, well, what happens for values of y as x gets large? Okay? Actually, plus or minus infinity. But in this case, I just had to look at plus infinity. Okay, so now let's look at problem number 11. Well, notice as x goes to infinity, for x large, I have a 6x squared minus 2x minus 8. That's very close to 6x squared. Over 2x squared minus 8x plus 4. That's very close to 2x squared, which is the x squared is canceled, 3. Therefore, the horizontal asymptote is just y equals 3. So if you come out that for large values of x, your y value approaches a number, that number is the horizontal asymptote. Okay? So if you happen to look at just the ratio of the leading order terms and let that go off to infinity, that will tell you if you have a horizontal asymptote or not. And if that ratio is a constant, then that's your horizontal asymptote. Okay, so let's look at this. As x goes to infinity, well, x squared minus 2 approaches x squared. 4x minus x to the fourth goes to a negative x to the fourth. And so this, well, if I simplify this, is the same as negative 1 over x squared. And as x goes to infinity, 1 over x squared goes off to 0. It keeps getting smaller and smaller. So this whole thing goes off to 0. Therefore, the horizontal asymptote is just y equals 0. Any questions about that? Yeah, it approaches the x-axis. Mm-hmm. So somehow it'll wobble around, but eventually it just peters out to the x-axis as x actually goes to plus or minus infinity. I'm just saying, you know, even though I'm just saying infinity, it's actually plus or minus infinity. Okay, give the equation of the oblique asymptote, if any. So to find the oblique asymptote, what I want to do is simplify this function. So let me do that. I don't need too much room. So 13. So I have f of x equal x squared minus 5x plus 7 over x plus 3. So let me do synthetic division. So let me just write down the coefficients. 1 minus 5, 7 for the dividend. And setting x plus 3 to 0, I get a root of negative 3. Let me drop down the 1 times negative 3 is negative 3 minus 5 is a negative 8. Times negative 3 is 24, plus 7 is 31. Okay, so doing that, I see that this is 13, right? I see that this function can be written as x minus 8 plus 31 over x plus 3. So now you notice that this last term here goes off to 0 as x is very large. And so that means that in this case, we can neglect this last term. And so the oblique asymptote is just this quotient. So really, all they're asking you for is the quotient. And so when they say find the oblique asymptote, just find the quotient. However, it's the exact same way we did it back in Math 125. Okay. Now they're asking you to graph. So graph these functions. Okay, so let me go up here so I can get a new page. Okay, so let's, no, you don't need to. It wouldn't be wrong. Okay, so let's graph y equal x over x squared minus 49. And so I'll write that as x minus 7, x plus 7. So first, let's find the vertical asymptotes. And so I'll set each factor in the denominator to 0 and solve for x. So x is 7, x is negative 7. Okay. Next, let's look for the horizontal asymptote, if it exists. And so I have here that y is equal to x over x squared minus 49. And so this approaches for x large. Well, this is going to be the same as x over x squared, which is 1 over x squared, 1 over x. But this term is going to go off to 0 as x goes to infinity. And so this approaches 0. And so the horizontal asymptote is y equals 0. Okay. And maybe I'll find one other. So let's see that. Let's get an x-intercept, which actually also will be a y-intercept. And so to find the, well, let's say the y-intercept. To find the y-intercept, I'll set x equal to 0. So the y-intercept is at 0, 0. Therefore, the x-intercept is also at 0, 0. Okay, so we have 1 point. So let's graph this. Okay, so 7. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 7. Okay, so I have x equal negative 7, x equal positive 7. Those are my vertical asymptotes. I have y equals 0. Here's my horizontal asymptote. It passes through 0. Okay, so I guess I should note some signs. Ooh, I don't have a lot of room left. Okay, so note that if x is large, meaning if x is greater than 7, let me just put some pluses and minuses here. So now I'll just erase them. So notice if x is greater than 7, then, well, x is positive. And if x is greater than 7, well, x minus 7 is positive. So is x plus 7. So I have 3 positives So this is all going to be a positive. So that means that somehow it's up here. Between 0 and 7, well, uh, this is going to be positive, negative, positive. And so positive over negative times positive is negative. Actually, all the roots are simple, so I know that it alternates in sign. And so that means that somehow things are in this region up here, down here, up here, down here. Okay, so now let me get rid of the pluses and minuses. Notice that it passes through here. Okay. And it has to go up here, down here, and it has to be blocked by these. So it has to look something like this. It has to go off to infinity here and down to infinity here. Next, it always has to be in this region here. It is blocked by these two asymptotes, so it's got to go to infinity here and has to go to 0 here. So it has to look something like this. Oh, by the way, this is also an odd function, so it has to have symmetry. So things have got to look like mirror images of each other. So if you notice that these look like this looks the same as that, you just sort of flipped it over, and this looks the same as that. Hopefully, you just flipped it over. So there's some symmetry here. Okay? And that's what the graph looks like. Any questions about that? Oh, the horizontal asymptote. Oh, so I'm looking at very large values of x. So if x is very large, then this just looks like 1 over x. But if x goes infinity, what's 1 over a million? That's pretty small. What's 1 over a billion? That's even smaller. So as x goes infinity, 1 over x goes to 0. Therefore, eventually, my y values for large values of x eventually go off to 0. So that's why this peters out here. Okay? So that's why this is a horizontal this x-axis is a horizontal axis, is the horizontal asymptote. Any questions about that? Okay. Yeah, so for this problem, there were a lot of details we had to look over because you have to graph everything. Okay, 15. Well, we have to do the same thing. So there's going to be some work here. So, oops. So 15, x squared, 32, and 30. So f of x equals x squared plus x minus 42 over x squared minus x minus 30. Okay, so let's simplify this. That's factor. Bring down the plus. Times minus is minus. I want two whole numbers whose product is 42 and whose difference is 1. So it's 7 and 6. Again, I have a nice monic polynomial. Bring down the minus. Times minus is plus. I want two whole numbers whose product is 30 and whose difference is 1. So 6 and 5. So now, notice I can cancel these. But I'm going to have to make a notation here because I'm changing my domain. So it's x plus 7 over x plus 5 so long as x is not equal to 6 because I canceled the x minus 6's. So the domain changed. So that means that there's going to be a hole, and actually I'm going to say that here. There's a hole when x is 6. Okay, and so let's figure out what the hole is. So the hole is when x is 6. Let's figure out what y is. Well, y is x plus 7 over x plus 5. So that's 13 over 11. So there's a hole at 6, 13 over 11. So I'm going to have to be sure that I put that hole in the graph. Okay. But now I can graph x plus 7 over x plus 5. So let's do the vertical asymptote. So to find the vertical asymptote, I'll set the denominator to 0. So x is equal to negative 5. Let's do the horizontal asymptote. And so I have y is equal to x plus 7 over x plus 5. And so as x goes to infinity, well, again, this is just a ratio of 1 over 1, so it'll be 1. But as x goes to infinity, x plus 7 is very close to x plus 5 is very close to x, which is 1. And so the horizontal asymptote is y equal 1. I guess let's look for the x-intercept. Found by setting the numerator to 0. And so I have x equal negative 7. And lastly, I guess I'm running out of space already. These are bigger problems. Oops. Let's go further down. Oh. So I set the numerator to 0. So I set I set the numerator to 0, and so subtract 7 from both sides, so x equal negative 7. Next, let's find the y-intercept. And so I can find the y-intercept by letting x equal 0. And so the y-intercept is 0, 7/5. Okay, so that should be everything. So now I should be able to graph this. Okay, so let's see if I can remember everything. So that's 6 and 7. So it's again pretty big. 1, 2, 3, 4, 7, 8, 9, 10. Be sure that you try to make these tick marks relatively the same size, both in the on the x and y axis. Okay, so let's see. Hole at, well, let's do the vertical asymptote is negative 5. 1, 2, 3, 4, 5. So that's my vertical asymptote. I have a horizontal asymptote at x equal 1. Y equal 1, of course. It's a horizontal asymptote. I have a y-intercept at negative 7, x-intercept at negative 7, a y-intercept at 7/5, so that's just about here, And I have a hole at 6. 1, 2, 3, 4, 5, 6. So I have a hole here. Okay, so the graph should look like, well, we just connect. Notice that I eventually have to peter out so it looks like 1, and I have to blow up at -5, and I have to pass through this point here at -7. So it has to look something like this. Next, I have to eventually go to 1, but I have to blow up here at -5, and I have a hole here. So connecting all these, yeah, and eventually approach that. I sort of missed a few things, but good enough. Uh, okay, there. That actually looked a little bit better. Okay, so that's what the graph looks like. So notice there's a hole here at 6, 13 over 11. Okay, and that's your graph. Any questions about that? Yeah. So there's a hole. So in other words, it keeps approaching this, but obviously it can't. There's a hole there, so it just at that one point. So it goes like this, but there's this little bitty hole there. It doesn't quite get. Now, of course, we're exaggerating, saying it's a huge hole, but it's really just a little bitty dot. It's one point. Okay. Okay. 16. Question. Say again. Yeah. Yeah. Okay. Yeah. But it's not. I don't think it's too hard. Well, I don't know. Let's see. Well, let's check. Okay, let's check. Okay, so the concentration. Yeah, so the concentration of a drug in the bloodstream measured can be modeled by this function where T, when will the drug be? Oh, we'll skip that one. Yes, okay. Yes, okay. That's a wrong problem. You need calculus for this. Okay, so let's not do that one. 17. Solve the inequality. Yes, we offer Calc 1, Calc 2, um, every semester so far. And it's usually around like 8 a.m. in the mornings, from like 8 to 8:15, I think, to 10:50, Monday through Thursday. Okay. So let's solve this inequality. Okay. So let's first find the critical values, the critical numbers, found by setting each of these to 0. So x equal -3, x is 5, and 0. So let's place each of these on the number line. -3, 0, and 5. Okay, so now notice that each of these have multiplicity of 1. So that means that they're going to alternate in signs. Okay, so let's take a number bigger than 5. Let's say 6 as a test number. 6 is positive. 6 plus 3 is positive. 5 minus 6 is negative. Positive times negative is negative. Okay, any questions about that? Yeah, and you could choose any number greater than 5. Doesn't matter. Now, because these all have a odd multiplicity, then it alternates in sign. If they had an even multiplicity, then when you cross that root that was even, these signs wouldn't change. But since they have odd multiplicity, the signs change. And so we want this to be greater than 0. So I fill in the plus. We want this to be greater than or equal to 0. And so I fill in the critical numbers also. And I fill in every critical number because my expression is defined everywhere. And so this is negative infinity to negative 3, union 0 to 5. And that will be my answer. Any questions about that? No. Okay. So now, let me do 18. I might be able to do it here. Okay, so let's find the critical numbers. Found by setting each factor to 0, both for the numerator and for the denominator. So x is equal to negative 9, positive 2, and positive 1. So let's place these on the number line. Negative 9, positive 1, positive 2. Let's plug in 0, because 0 is a nice number. So 0 plus 9 is positive. 0 minus 2 is negative. 0 minus 1 is negative. Positive times negative divided by negative is positive. And so in this region, it's that's where the 0 test point is. It's positive. If I can pick 0 as a test point, do it. The only time you can't pick 0 as a test point is when it's one of the critical numbers, which I couldn't do above. So now notice that all the multiplicities are 1, therefore everything alternates. So minus, plus, minus, plus. Yeah, the powers of these factors. Okay, so now we want this to be greater than 0. So I fill in the plus. I want it to be greater than or equal to 0. So I fill in all of the critical numbers except for those critical numbers found by setting the denominator to 0. I set the denominator, x minus 1, to 0. So when x is 1, I do not fill in the critical number. And so I fill in these other two critical numbers, but not the one at 1. And so for problem number, was it 18, the answer is negative 9 to 1, but not including 1, and from 2 to infinity. And that is your answer. Any questions about that? Okay, good. Okay, we'll certainly need a fresh page for this one. Okay. Use the factor theorem. Ah, to determine. Oh, okay. Well, no, that's actually relatively short. Uh, Use the factor theorem to determine whether x minus c is a factor of f of x. Okay. So for problem 19, the question is x plus 12 a factor of x to the fourth plus 12x cubed plus 5x squared plus 51x minus 108? So all you have to do is check, is negative 12 a root of x to the fourth plus 12x cubed plus 5x squared, good grief, plus 51x minus 108. And this is, the root is negative 12. And so let's see, 4, 3, 2, 1, 0. Yep, they have everything. So now let's check if it's a root. And so just use synthetic division. Drop down to 1 times negative 12 is negative 12. Oh, that makes it nice. They get 0. 12 minus 12 is 0. Times negative 12 is 0. Plus 5 is 5. Minus 12 is a negative 60. Minus 51 minus 60 is negative 9. Times 12 is going to give you a positive 108. So you get 0. So you have no remainder. Therefore, yes, by the factor theorem, it is a factor. So yes, x plus 12 is a factor of f of x. That's all you have to do, yeah. Because you're using the factor theorem. So that's nice. Let me do problem number 20. Uh, well, for problem 20, it says the exact same thing. And so we're going to do the exact same thing. So is x plus 4, pardon? Um, well, yeah, I mean, I would say that because there are a lot of interesting problems you can do without calculus involving polynomial functions. And so because of that, in pre-calculus, they look at polynomial functions. It turns out that once you have calculus, you can answer all these questions and many more for any sort of function. And so without calculus, we're sort of limited to asking a lot of these questions um, looking at polynomials. But we can actually do a lot more with polynomials because they're relatively simple. Okay, so let's see if this is a factor. And so x plus 4. So setting that to 0, get x equal negative 4 is 5x to the 4 plus 19x cubed minus 4x squared plus x plus 4 is negative 4, a root of this. If negative 4 is a root of this polynomial, then x plus 4 is a factor of the polynomial. So bring down the 5 times negative 4 is negative 20. Um, Plus 19 is a negative 1 times negative 4 is a positive 4. Plus, so 4 minus 4 is 0 times negative 4 is 0. Plus 1 is 1 times negative 4 is negative 4 minus 4 is 0. So the answer is yes. Again, yes, x plus 4 is a factor. of my function. Okay? Any questions about that? Okay. Let me do problem number 21. List the potential rational roots, rational zeros of the polynomial function. Do not find the zeros. So it's just asking you to list them all. Right, right. Okay, so first let's find the factors of, in this case, 6. So what are the factors of 6? Well, actually, maybe we call those Q. The factors of 6 are 1, 2, 3, and 6. Let's find the factors of 2, 1, and 2. And wait 1 second, let me just check something. Okay, so it's Q over P. That's the usual notation. So the usual notation for the rational root theorem is Q over P. That's what I actually. So I'll tell you how I cheated to figure out because I can never remember these. And so what I did is I said, well, look, suppose I have some linear function, px minus q equals 0. Then I want to figure out all roots of that. Well, set that to 0. So you add q to both sides, divide by p. Therefore, x is equal to q over p. And so the roots must be of the form q over p, where q, where p was the leading order coefficient, and q was um, the term in the constant term. So I labeled those wrong. So it's pq. So p was uh, the factors of 6, and q were the factors of 2. So let's do that. And so uh, the factors are, well, I can divide everything by 1, so that's plus or minus 1, plus or minus 2. I can divide everything by 2, so that's plus or minus, 1 half. 2 divided by 2, well, I don't have to do that. Uh, plus or minus 3 halves. And, wait, I just did it wrong. This is Q over P. So plus or minus 1/3, plus or minus 2/3, plus or minus 1/6, plus or minus 2/6. Again, that we don't have to do that one. Anytime they have any sort of simplifications, you don't have to write it because it'll already be in the list. And so these are the possible values that we'll have to look at. So there are 2, 4, 6, 8, 10, 12 numbers there are only 12 numbers that could be roots of rational roots of this particular polynomial. So that's it. Any questions about that? Okay. I guess I should have written the Q first. I'll do that next time. Okay, so in problem 22, use the rational zeros theorem to find all real roots of the polynomial. Use the zeros to factor f over the real numbers. Okay, so let's try to do that. Oh, but that's going to be a nice one too. Okay, so pardon? Q. Well, I did because I did. So I divided plus or minus 1 by 1 by 2 by 3 and by 6. I divided the 2 by 1, 2, 3, and 6. So I did include all the ratios. No, or nor 6, because they're in the denominator, not in the numerators. Okay, so let me do 23. So f of x equal x cubed plus 2x squared is 18. Okay, so let me write down q. So the factors of 18 are 1, 2, 3, 6, 9, and 18. So those are all the factors of 18. The factors of 1 are, well, just 1. Okay, so let's find the uh, Q over P. Okay, and so if I look at this, well, divide each of these by 1, well, I get the same list. 1, 2, 3, 6, 9, and 18. So these are the only possible roots of my polynomial. Rational roots, I'm sorry. These are the only possible rational roots of my polynomial. So let's try -2. Why -2? Because I can already see it's a factor. Because, oh, and 3, I think. Because if you look here, this is 1 and a 2, and then this is ratio, 9 to 18 is a 1 to 2 ratio. And so x plus 2 has got to be a factor. So -2 has got to be a root. So let's check if our guess is correct. So that's 1, 2, -9, -18. Bring down the 1 times -2 is -2, so you get 0. Times -2 is 0. Minus 9 times -2 is 18. Minus 18 is 0. Good. So that factors. Next, let's try 3. Drop down the 1 times 3 is 3, plus 0 is 3, times 3 is 9, minus 9 is 0, and lastly, try -3. So you get 1 times -3 is -3, plus 0, plus 3 is 0. And so the roots are 0 to factor f. And so the roots are -2 plus or minus 3, but it also said the factor. So f of x is equal to x plus 2 times x minus 3 times x plus 3. Since I already have listed all the roots. And this is a monic polynomial. Any questions about that? No. Oh, these are the roots. It said to find all the or zeros. It said find all the zeros. So these are the zeros of your function. So x equaling -2 plus or minus 3 are the zeros of your polynomial function. Okay. Let's do problem number 23. And so 5x to the 4 minus 20x cubed plus 21x squared minus 4x plus 4. Okay, so let's figure out what q is. So the factors of 4 are 1, 2, 4. Factors of 5 are 1, 5. Q over P. And so let's divide everything by 1. By 5. Okay. So 5x to the 4 minus 20 plus 21 minus 4 plus 4. It almost looks like one of the fifths. Okay, so if I look here, 1, so at 0 it's positive. At 1 it's going to be, that's a negative 24. Oh, it's still positive at 1. Okay, so it's still positive. Oh, so let's try it 2. So that will give us 2. Let's try 2. See if that works. That does anything. 5 minus 10 gives you a negative 10. Negative 20 gives you a 1. Which gives you a 2, which gives you a negative 2, which gives you a negative 4, which gives you a 0. Okay, so 2 works. Okay, so 2 is a factor. Probably a negative. Negative 1/5 or something. Don't know. I'm just guessing. Okay. So this is just a guess. I have no idea if this will work. But if I get a fraction, I know it's wrong. So 5, that gives you a negative 1. So wrong. Can't do it. Okay, so I know that I can't do that. All of a sudden it's wrong because I'll get a negative 1, which give me a negative 11, and then that's not divisible by 5. Okay, so let's try 2, which will give me 12. So that doesn't work. And 4 would give you 14. So none of the fractions work. So I know none of the fractions work. Okay, so let's try a negative. Pardon? Yeah, let's try something like negative 2. Okay, so 5. That'll give me a negative 10. That's a negative 20. Too big. Too big. 4. 4, 2. Okay, so here, wait. Oh, this is a ratio of 1 to 2. Stupid. 2 works. Not negative 2. 2 works. That works. It's a ratio of 1 to 2. Okay, so 5, 10, 0, 0, 1, 2, 0. Ah, okay. And then that's going to be square root of 5. Okay, so this goes, and you want to factor it over the reals. Okay. So now I have a 5. The reduced equation is 5x squared plus 1 equals 0. Oh, but you can't factor that over the reals because that'll give you a negative 1/5. The square root of negative 1/5, so that'll give you an I. So I guess we can't factor that anymore over the reals. And so the real roots, it said use it to find all real roots. And so the real roots are x equal 2. And so this factors into x minus 2 quantity squared times 5x squared plus 1. And you only want to factor, I guess, over the real numbers. So factoring over the reals gives you this. If you could factor further if you're going to factor over the complex numbers. But he only wanted to factor over the reals. Any questions about this? Oh, yeah, from this reduced equation here. So I have, this is 5x squared plus no x plus 1 with a remainder of 0. So that was my reduced equation. Okay. Find the intercepts. Okay, so let's do that. I can probably do that here. Oh, well, except, okay, so let's do 24. So f of x equals x cubed. So let's actually factor this by grouping. X cubed plus 3x squared minus 4x plus 12. So that's equal to x squared x plus 3 minus 4x plus 3. So that's x plus 3 x squared minus 4. So that's x plus 3 x minus 2 x plus 2. Okay, so it says to find the intercepts. So let's find the x-intercepts found by setting each factor to 0. Well, x is negative 3, positive 2, negative 2. Find the y-intercept. And so by setting x equal to 0, well, if you plug x equal to 0, you get 0 plus 0 cubed plus 3 times 0 squared minus 4 times 0 minus 12. So y is negative 12. So the y-intercept is at 0, negative 12. And you have 3 x-intercepts at negative 3, 0, 2, 0, negative 2, 0. Any questions about that? Oh, right. Um, you can see that you can factor this by grouping. So I grouped the first two terms and the last two terms. But since there was a minus sign, I had to change this minus to a plus. And then I noticed I have an x squared in common and a 4 in common. And now I have an x plus 3 in common, so I factor it out. And what remains is x squared minus 4. But I can factor that by a special product formula as x minus 2 and x plus 2. And then I just set each factor to 0 and solve for x. Just set, yeah, maybe I should, let me add another page so I can actually do this. Okay, so let me do this. I was trying to cram it in too compactly. Okay, so let me do problem number 24. So 24. So f of x is equal to x squared, x cubed, plus 3x squared minus 4x minus 12. So you want to find first, let's say, the y-intercept. To find the y-intercept, you just set x equal to 0 and solve for y. And so the y-intercept is at 0, negative 12. To find the x-intercept, you just set this equation equal to 0 and solve for x. And you can do that several ways. You could have either done it using the rational root theorem like we did above, or in this case, notice that it's really easy to factor by grouping. So I grouped the first two terms, and I grouped the last two terms. But since I had a minus here, it changed this plus 4x to minus 4x, and this plus 12 to minus 12. Now, I notice I have a x squared in common, and I have a 4 in common. Factor out the x plus 3. What remains is x squared minus 4. And I can factor this even further if I wanted to into x minus 2x plus 2. And so from there, I set each factor to 0 and solve for x. So x equal negative 3, positive 2, negative 2. And so the roots, the x-intercepts are at negative 3, 0, 2, 0, negative 2, 0. So those are my three x-intercepts. Any questions about that? Yeah. Okay. Let's do, yes, that was kind of crammed in too much. Okay, problem number 25. Luckily, they've already factored it for us. So f of x equal x minus 3 squared, x squared minus 16. So let's find the y-intercept. And so let's plug in for x 0, me get another page. Okay, and so I have negative 3 squared is 9 times negative 16 is negative 144. And so the y-intercept is at 0, negative 144. Let's find the x-intercepts. We can find the x-intercepts by setting y equal to 0. So x minus 3 squared is 0. X squared minus 16 is 0. So x is equal to 3, or x squared is equal to 16. So x is equal to plus or minus 4. So the x-intercepts are at 3, 0, 4, 0, negative 4, 0. So I have 3 x-intercepts. Any questions about that? Right. And so uh, if x squared is 16, then x is equal to plus or minus 4. And the fact that the 3 was a double root, we really don't care about. Right. Mm-hmm. Okay, so let's do problem 26. The following information is given about a polynomial whose coefficients are real numbers. Find the remaining zeros. So I have that the polynomials of degree 3, and the zeros are 4, and 1 minus I. Well, since the coefficients of the polynomial are real, then I know that uh, the roots come in conjugate pairs. And so the conjugate of 1 minus I is 1 plus I. And so I now have 3 zeros. It said find the remaining zeros. Then that's it. That is the remaining zero. 1 plus I. Any questions about that? Sure. It's because we have a 1 plus I. I'm sorry, a 1 minus I. So what's the conjugate of 1 minus I? Well, you just change the sign in front of I, and that's it. And so as long as the coefficients of your polynomial are real, then I know that they come in conjugate pairs. Since I have 1, 2, 3, 3 roots, 3 zeros, then I found all zeros to my polynomial of degree 3. Let me do problem 27. The degree is 4, and my zeros are 5 minus 5i and 7i. Again, since the coefficients of the polynomial are real, then the roots have to come in conjugate pairs. And so if 5 minus 5i is a root, then 5 plus 5i must also be a root. You just change the sign in front of the I. Similarly, since 7i is a root, and since all the coefficients in your polynomial are real, then negative 7i, the conjugate, is also a root. Since there are 1, 2, 3, 4 roots, and the degree of the polynomial is 4, I have found all the roots. And I am done. Any questions about that? So, right, if you have a 5 minus 5i, then you must also have a 5 plus 5i. That's why a lot of times we write the roots like a plus or minus. Okay? So they always have to come in conjugate pairs. So the roots would be, you know, 5 plus or minus 5i and plus or minus 7i. Any questions about that? Okay. Let me do problem number 28. So the degree of the polynomial is 3, and the zeros are negative 3, 3 minus 2i. Form a polynomial with real coefficients having given degree and zeros. And I'll assume that we want a monic polynomial. Well, if I have real coefficients, then not only is 3 minus 2i a root, so is 3 plus 2i. So now my polynomial must look like x minus a negative 3, x minus 3 plus 2i times x minus 3 minus 2i. Okay, so this is equal to, well, x plus 3 times x minus 3 minus 2i x minus 3 plus 2i. So f of x is equal to x plus 3 times, this is special product formula, so this is x minus 3 squared minus 4i squared, which will give me a plus 4. Because I squared is negative 1. Therefore, negative I squared is a plus 1. And so, let me insert another page. And so I have f of x is equal to x plus 3 times x squared minus 6x plus 9 plus 4, x plus 3 times x squared minus 6x plus 13. Let me multiply x 3 inside the parentheses. So I get x cubed minus 6x squared plus 3x squared plus 13x minus 18x plus 39. So I get f of x equal x cubed minus 3x squared minus 5x plus 39. And that is your answer. Any questions about that? So that's a monic polynomial, which is of degree 3, having negative 3 as a 0 and 3 minus 2i as a 0. Mm-hmm. Yeah, so I just distributed it to simplify it. Yeah. Combine like terms and all that. hmm Okay, let me do problem 29. The degree is 4, and the zeros are -1, 2, 1 minus 2i. Well, if 1 minus 2i is a root, so is 1 plus 2i. Okay, so the polynomial, again assuming it's monic, is got to be, well, the root is -1, so I have a factor of x plus 1. I have a root of positive 2, so I have a factor of x minus 2. I have a root of 1 minus 2i, and so I have a factor of x minus 1 plus 2i, and x minus 1 minus 2i. So let's simplify this. So if I multiply out these, I get x squared plus x minus 2x is minus x minus 2. And I get x minus 1 plus 2i times x minus 1 minus 2i. So this is equal to x squared minus x minus 2 times, again, this is special product formula, just like above, x minus 1 squared minus 2i squared, which gives you a plus 4. And so I get x minus x squared minus x minus 2. Let's multiply this out again by the special product formula. So we get x squared minus 2x plus 1 plus 4. Ugh. X squared minus x minus 2 times x squared minus 2x plus 5. So multiply this out. So let's multiply all this. And so I get, oops, x4 minus 2x cubed minus x cubed plus 5x squared plus 2x squared minus 2x squared x. So that would give me minus 5x plus 4x. And then lastly is the constant minus 10. Okay, so let's see. That's 3, so gives me 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and so I get f of x, combining like terms now. F of x is equal to x to the fourth minus 3x cubed plus 7x, no it's not, plus 5x squared minus x minus 10. And that is your answer. So the hardest part in this is probably multiplying everything out. Ensure you don't make an error because there are a lot of terms here. So you just use distributive property and then combine like terms. Okay, so Let's do problem number 30. So use the given 0 to find the remaining zeros. Okay, so I have f of x equal x cubed plus 5x squared plus 7x minus 13. And so I have 1, 0. This is a cubic. Oh, okay, so I have to have a rational 0 then, because it's going to be, so how about 1? Okay, so let's do this. Okay, so I have here, I have 1, 0 being negative 3 plus 2, I'm sorry, plus 2i. Therefore, I have another 0 being negative 3 minus 2i. Okay. Well, the only possible roots are plus or minus 1 and plus or minus 13. Yeah. So if I notice here, the only possible roots are 1 and 13. But maybe what I'll do is I'll try 1, see if 1 works. It does. 1x cubed, 5x squared, 7x minus 13. And so I get a 1, 6, 13, 0. Oh, okay. And so, therefore, the roots are x is equal to 1, x is equal to negative 3, plus or minus 2i. So that gives me all 1, 2, 3 roots of my polynomial. And that's it. Those are the 3 roots of your polynomial. So we found the additional. Any questions about that? Okay. Okay, sure. Hmm. Okay, so I want to evaluate the expression using the given values in the given table, using the values in the given the table. So f composed with g at 6. So first, I'm going to plug in 6 to g. I get output of 11. I use that as the input for f. The output is 3. And so f composed with g at 6 is 3. And I'm done. So that's all you had to do for that particular problem. Okay? Sure. Right. Yeah. So you see that I have here a 6 and it's a G. And so for G, I input 6, the output is 11. But I then input 11 for the F and the output is 3. Therefore that's the answer. And so I input 6 for G, I get output of 11, input that for F, the output is 3, and that's my answer. Okay? Yeah. Okay, let me do problem 32. So you want to, maybe I'll just do it over here so I have some space. 32. So I have f of x equal x minus 6 over x, g of x equal x squared plus 9. I want to compute g composed with f at negative 2. So first, compute f at negative 2. So I'm going to replace x here by negative 2. So you get a negative 8 over negative 2, which is positive 4. Now I'm going to plug that into g. So you get 4 squared plus 9 is 25. So g composed with f at negative 2 is 25. Any questions about that? Right. So let me do this. So I have a negative 2. I'm first going to plug it into, oops, there's f first, into f. And then I'm going to plug that, whatever answer I get, into g. So I plugged negative 2 into f, and I got 4. I then plug the 4 into g to get 25. And that gives me my composition. So you first plug in the negative 2 to f. Whatever output you get, you plug that into g. The output for that is your answer. It's 4 squared is 16. Okay. Okay, so you want to find the domain. Okay, so let's do that. Yeah, I don't have enough room there. Okay, so I can probably squeeze it in here. Okay, so I have here F composed with G. So wherever I see an X in the formula for F, I replace X by the formula given by G. So -7 over X, which is a -3 over X, plus 1. Now, when finding the domain of a composite function, don't simplify. So don't simplify this. Uh, and so, because whenever you simplify, well, whenever finding any domains, don't simplify because you'll change the domain. Okay, so I want to set the denominator to 0. So set x to 0. That's one part of the domain. And you want to set -3 over x plus 1 to 0. So multiply everything by x. So you get -3 plus x is 0, so x is 3. Oh, so the domain of f composed with g is a set of all x's except for 0 or 3. So it is the interval from -infinity to 0, 0 to 3, and 3 to infinity. Now, I'll never fit that in there. -infinity to 0, 0 to 3, and 3 to infinity. So that's the domain of your function. Well, I multiplied everything by x to get rid of the denominator, to make that rational equation into a linear equation. Well, I had to have that. I didn't want to divide by 0, so this denominator couldn't be 0, and this denominator could not be 0. So I actually had sort of two denominators. Okay. Okay. Let me do problem number question. Right. Well, it depends on what they want. So you can look at the answer, see how it was written. So either way is okay. It depends on just the way they want it to be written. Okay, 34. F composed with G at x. So wherever I see an x in F, I replace x by the formula given by G, 4 over x plus 5. So I have x, 4 over x plus 5, divided by x, 4 over x plus 5, plus 1. So I want to find the domain. So I set the denominator to 0. Well, x plus 5 to 0. And I set the denominator 4 over x plus 5 plus 1 equal to 0. So those are the only denominators we have, even though the x plus 5 occurs more than once as a denominator. So x equal negative 5, or multiplying both sides of my equation by x plus 5, I get 4 plus x plus 5 is 0, so x is negative 9. Yeah, I multiply by x plus 5. And so the domain is set of all x's not equal to negative 9 nor negative 5. So it is the interval from negative infinity to negative 9, negative 9 to negative 5, negative 5 to infinity. And that's your domain. Any questions about that? Okay. So, evaluate the expression using the graphs of f and g. So I'm assuming I can see good enough to do this. Okay, so f composed, so this is 35. So f composed with g. No. Is that composed or is that multiplication? Yeah. Maybe that is multiplication. I don't know. Um, Actually, I will. What's the answer? Look up the answer. What's the answer to problem 35? do you, yeah, do you have the answer there? 3. 3. So let me just check. So at negative 1, at negative 2, it's going to be 1. Oh, it is multiplication. Okay, so it's multiplication. So f times g at negative 2. Okay, so we want to do f at negative 2 times g at negative 2. And so if I plug in negative 2 here, well, it looks like it's equal to 1 for, for g and 3 for f. So it's 3 times 1 is 3. And that's your answer. Okay? I just looked here on the graph, and I saw that when x is negative 2, when x is negative 2, f is 3. When x is negative 2, g is 1. And just multiply those two numbers together. 3 times 1 is 3. Okay? 36. I'll draw the inverse. Okay, so let's do that. And so, 36. The graph, I'm going to do this kind of crudely. graph here of the square root of x plus 2. So this is going to be the graph of the square root of x plus 2. Okay? So now what we want to do is we want to invert this. Okay, so here's the line y equal x. And I'm going to flip this over, okay, so that it looks like the same thing on the other side. So it should look something like this. So this is the graph of y equal f inverse. So this negative 2, no, it's respect to this line. So this distance here should be the same as this distance. This distance here should be the same as that distance. And so now, of course, I wasn't so good here because these have got to be obviously cross at this there. Okay, so now it looks obviously this. So this distance same as that distance. These are all the same if you go perpendicular. Actually, now it sort of looks correct. So now it looks a little bit better. There. That's actually looking a little bit better. Another way of doing this is if you have a piece of paper, draw this. The square root, of course, I should draw it better, but draw the square root of x plus 2 and put x, y. And then when you look, when you turn, you look at it through the back side. So, you know, put your paper up to the light and look through the back of it. If you look at the back, and now if you place y where x used to be, and you place x where y used to be, so the axes are inverted, then you'll see that the graph looks like this. You'll always get the graph of the inverse function by just interchanging the x and y axis. That's another way of graphing it. Any questions about that? Okay. Um, Here's a question. Can we continue this in about 2 hours or so? Yeah, like an hour or so, because I'm getting a headache. So I'm gonna take something. I'm gonna take something. Okay. Okay. Yeah. So let me take a break. So I'm gonna end this, and then I'll contact you when my headache is better. Okay. I'm gonna take something. Okay. Okay. Bye bye.